Hey, good afternoon, and thank you very much, Eric, for the very nice introduction. Thank you very much, all of you, for having me over here and for listening to me after lunch, which I know is always a tough task, so I'll try to make this as entertaining as possible. Actually, I'm currently a co-director of a graduated engineering research center, and you'll see that we go back to 2003. So, I had actually quite a bit of a pleasure of looking back to some of the stuff we did more than 10 years ago and try to give you some, feedback or give you some of the lessons or tell you some of the lessons we learned in our engineering research center. A little bit of an advice and a heads up, this was a Generation 2 engineering research center, so some of the things have changed. I would say not too drastically, but, we operated under slightly different conditions than the ones who are looking for proposals right now will be in the future. So thank you everyone for having me. Thank you for NSF for inviting me. It's a pleasure. It's been a wonderful time working with NSF. In the Engineering Research Center, we are graduated now, as I said, but it's also a wonderful time continuing to work with NSF because we have been lucky enough to have continuing grants from other areas that support our work, and I'll tell you a little bit about this. So what I'd like to do is, I'm an engineer, so my talk is going to be quite different from what you heard in the morning from these people who really do research on teams, on the economics, on research and all the stuff. For me, it's probably more a little bit of a boots on the ground report here. But I want to give you, first of all, an overview what CASA is about, and then tell you a little bit about the lessons we learned. So ours is actually all about weather. And so you see already where the convergent research comes in, right? Because there's social, societal, socio-economic impacts. Everyone gets up in the morning, checks their weather. Everyone looks for how to dress their kids. Everyone talks to their colleagues. How hot it is in DC these days, and all these kind of things. And you'll see that there's a lot of much far-reaching impacts. So CASA was awarded in 2003. It was a collaboration between University of Massachusetts Amherst, Colorado State, the University of Oklahoma, the University of Puerto Rico, where I don't have you guys on there. You're coming down the next slide, sorry, but Sandra Cruz-Paul, who's now at NSF, was part of the center, University of Colorado, Colorado Springs, University of Delaware, and members came and left over the time. And we started, doing, if you have weather, you have to have test beds, right? You have to observe the atmosphere and get information out to the public. So we had a test bed in Oklahoma very early on, and now have still a test bed going on in Dallas-Fort Worth, and I'll tell you a little bit more about that. Again, our funding unfortunately ended in 2013, but we're now on a self-sustaining path and a pretty successful self-sustaining path going into the future. I want to do a shout out to Brenda Phillips, who is the other co-director of CASA. She's actually, her work is in resource economics, and I think she's really one of the driving factors for convergent research, because she always looks out to the impact on the resource side, on the economic side, on the end user side, and pulls the rest of the team towards we got to focus on that. We got to really, really focus on that. And if you deal with a bunch of scientists and engineers, you know how this goes, because everyone wants to look in their research and work on their stuff, and once in a while have to pull back to the surface and say, here's the big problem, that's what you got to work on. And that's really important. That's where, boots on the ground convergent research happens, is actually as a team, you have to look into how you get the end-to-end picture, how you have everyone working towards this end-to-end picture. So the end-to-end picture is now actually about severe weather warnings for floods, for tornadoes, thunderstorms, and looking into socio-technical systems, right? There's a lot of technology in what we're doing, don't get me wrong, but it goes out to the user. So one of the questions is, how do you give actionable weather warning information to the public, right? You can tell them that a tornado is coming, but early on when we did our studies, we had the folks from University of Delaware, from the Disaster Research Center, doing telephone surveys at the time. What do people do when they get a warning? They go outside and look if the tornado is really coming. Well, wrong decision, right? So how do you give people a warning? How do you give them to take the right actions, right? That's really part that's important in the research, besides a lot of the technical aspects. And we do this in a real world context, right? We have a test bed. I'll show you a little bit more about how this information goes out to National Weather Service, TV stations, emergency managers, and users in the end. And so now we're continuing on multidisciplinary research grants. We have grants from NSF. We work with the National Weather Service. We work with I don't know if I should say Raytheon or United Technology now. Things are changing so much in the private world. but we're working with them. They're one of the leading radar companies in the country, and we work with cities like the city of Fort Worth and the whole north central Texas region. Let me get to the motivation. Why did we even start the Engineering Research Center? So what you see on these slides is actually on the left-hand side, on your left-hand side is actually the coverage from the existing National Weather Service radars, the NEXRAD radars at 3,000 feet, 3 kilometers, sorry, 10,000 feet. I'm European, so I always get mixed up with the metrics, apologize. Now the funny thing is, or maybe a little bit counterintuitive, when you go lower, when you go down to 1 kilometer, 3,200 feet, your coverage gets a lot sparser. And why is that? Well, I'm actually famous for saying this in an NPR interview, the Earth is round, right? So if you have a radar that looks out straight or a little bit up, and you go out 200 kilometers, you overshoot quite a bit of the atmosphere. I'm sure everyone, or a lot of you came in by plane to this meeting. You know that, even by flying, that a lot of weather's happening fairly close to the ground. Once you're at 5 kilometers or whatever, you're almost out of the clouds, not too much is happening in this case. So, and that was actually also addressed by a National Research Council report, Weather Radar Technology Beyond NEXRAD is where is this going to go in the future in 2002. And so we picked up on that. And the idea is actually, well, what about if we build smaller radars and put them closer together? We can actually then do much better measurements because we can have radars overlap. That helps you on the technology side with better wind measurements. And we can look much closer to the ground. Right? So the left-hand side shows the system that's in place nationwide, and the right-hand side shows the system we proposed to build. And I want to say one thing. I always think about, can I find a better title for this slide, because it's NEXRAD versus CASA. That's not really the case, right? We're actually looking into having this complementary. Can we actually put systems like ours into areas where the coverage is not so well? I live in Western Massachusetts, where we have a NEXRAD radar in Albany, New York, and in Boston, Massachusetts, right? The lowest they're looking is 1,500 meters times 3, that's over 4,000 feet. It's the lowest the atmosphere gets sensed in our area, right? If you put a couple smaller radars in that area, you probably have much better weather information, much better forecast models, could give much better warnings. So the versus, if you find a better term, let me know. I'd like to stick it in this slide. So next generation warning systems. Another part of the motivation is actually look at the statistics, right? So first of all, we all make decisions about hazardous weather. Whole industry depends on that. Look at just, the airlines. We all have been sitting at airports when they're being closed because of weather and all this stuff. Over 80% of the US population is concentrated in cities. GDP, 80% of that goes in the United States is produced in metropolitan area. So, being more resilient in the face of severe weather is an important factor when it comes to, people living in cities, to, our economic strength and so on. So with that, we see that actually cities are more vulnerable, and that's one of the things we're focusing on. So with that, setting the stage, we want to build them. Our goal is to build hazard warning systems that aim to minimize death, injury, economic impact, property loss, help make infrastructure more resilient. There's a ton of different applications once you have that information, what you can do. Our research includes obviously sensors, right? You have to sense the atmosphere. We're talking about forecast. We're actually talking about also these days about nowcast, very short-term forecast in the hour of minutes. Networking and communication. I have this in red because this is my area. How do you get data from A to B? How do you do that if part of the infrastructure is impaired? Public safety, decision-making, and so on. That are all, components of this system. And now you see already that, you can think yourself of all the different research areas that come into play, right? And now how to get them to focus on this. I'll get back to this in a moment. We were lucky that, we had a really cool team with a lot of people doing a lot of hard work. David McLaughlin, our director at the time, really being a formidable leader. Building a system of radars. We had 4 radars out in Oklahoma. And this is a picture one of my colleagues came up with that shows you already what you can do just with a single radar by, looking closer to the ground, not so far out, and having a much higher resolution. On the left-hand side, you see an NEXRAD radar. And he said maybe we can portray this with, Mona Lisa and the resolution, right? Or think of any JPEG or any computer image and having a coarse grain resolution. And the right-hand side, a radar image from one of our radars having a much finer resolution. So you see much more detail. For those who come from Tornado Alley. You probably have all seen the hook echo. Actually, I have a laser pointer here. The hook echo down here, that is a very good indicator of a tornado forming. Actually, you see also this is a measurement from 3,000 feet above the ground. Here we are 800. So we have a much better idea where, whoops, going the wrong direction, where that tornado is. And that's actually what you see here also is an instantaneous image of that. And here's what the National Weather Service does is after a tornado has been reported a day or two later, they go out and look at the damage path, right? And that's the damage path, and you see how accurate our observations are on that. Interesting story about this here is what you can see, the NextGen radars update every 5 minutes, so you get new information every 5 minutes. With our system, we get every half minute, every minute updates. And based on an image for that tornado, or based on information they got from the National Weather Service, they made the projection that that tornado would move kind of this route. It made a slight left turn directly towards an emergency shelter, right? And so we got this information, and we could actually get information out to the people gathering outside, so is what they do, to tell them to go inside really quickly. So that had really some impact. And I want to show you on the next slide, actually, the system in operation. This is a little bit fast, so it's not every minute update, right? This frame is always a minute. How you can see how our system works, scanning the weather, the colored parts are different intensity of rainfall, hail in some cases here. And then what you see with these wedges moving fast is how we scan the atmosphere. So we don't scan it like you see in radar in the airport that always does a 360. We can actually focus. So we get really much better updates, much higher scan. And we don't scan areas where there is no weather. Right? So this is what we have developed in the time of the Engineering Research Center. There's a ton of results. I unfortunately don't have the time to talk about this in much detail. I'll be around a little bit afterwards, so I can answer, and I'll be happy to answer any questions you guys have on that. But a lot of studies, a lot of information going out to the end users, getting feedback from them, a lot of training with emergency managers, for example. So you show them it's radar data, but it's a new way of radar data with much higher update rate and so on. So they have to be able to interpret that data in the right way. So you have to go out and talk to these people. You have to talk to the weather service and so on, and I'll come back to some of the challenges on that in a moment. So, at some point in time, you're nearing the end of your engineering research center, right? And so you have to figure out what you want to do. And we got really lucky because we, the emergency manager of Fort Worth became aware of our work. And he came to one of our site visits. And he said, I want to have a system like yours in the Dallas-Fort Worth Metroplex. And we realized that for us to be sustainable, that is a much better area than southwestern Oklahoma, because there is just much more partners you can collaborate with and have a private-public partnership. And I think that was an important lesson. It's not necessarily about the research, but maybe something you want to already keep in mind right now, where you're really on the onset of, potentially having an ERC. Where do you go with that once the 10 years are over? That's a really, really important thing, and it's a really important thing to start thinking of that from day one. We weren't maybe doing the best planning. We got really lucky by finding Juan, who made us move our system out to the Dallas-Fort Worth area. And so we started what we call the Dallas-Fort Worth Living Lab. So we have a network out there that is centered around our radar technology we have developed, and includes other sensors. It's actually interesting to see that once in a while, industry comes and says, hey, can we put a soda out? Can we put a radiometer out? We have very sensitive barometric sensors out there, because they want to be out there to cross-reference measurements we have, right? So we have data from our radars, and they want to cross-reference it with some of the data they're getting there and getting them in. We want to benefit the characteristics of our system by showing high-resolution weather information that's high resolution in spatial and temporal, low observation, and we're looking into what impact does this have in an urban scenario where radar coverage is not necessarily as low as it could be, and what impact does it have on the users. Even there, it's multidisciplinary, right? We have electrical engineers, we have computer scientists, we have social scientists involved. I work with a colleague who is a hydrologist who looks into floods and flooding events, which happen quite a bit down in that area. And this testbed has then been created as a private-public partnership. And just to touch a little bit on that is, here's the whole spread of the areas we're looking in, right? So we're going from the sensors, from the sensors, I should show it this way, all the way to the value, right? So this includes quite a lot of areas. And I want to give you one example where being really convergent becomes important. And sometimes you're forced to be convergent, right? So you see here under dissemination, the second topic, there's something that's called AWIPS2, right? I actually have to look it up myself. It's the Advanced Weather Interactive Processing System 2. The Weather Service uses. The only thing National Weather Service forecaster looks at is information that he can access through AWIPS2. So we had to get our data in the process so it could be ingested and displayed through the system, right? If we wouldn't have done that, they wouldn't look at it, right? That's an important lesson you have to learn when you work with your stakeholders, right? And so everyone had to understand a lot of things because the folks who do the radar and do the signal processing have to understand, oh, this data now goes into a federal system. It has to go through a firewall, right? If you have high bandwidth data, how do you deal with that? What does the firewall do to that, right? We have new data that goes out to a forecaster. How does the forecaster interpret this data, right? So there's a lot of things that are not necessarily your core research, but that have an impact on how you design, how you implement your system, and a lot of challenges. Just giving you one quick example on that side. And you know, the really important thing is here, we have this living lab, right? It is running 24/7. It's giving weather information out of the Partnership for Innovation program. We have a grant where we actually built an application, a mobile phone app, where the data goes live to the users. We do some interesting research in how do we actually target the warnings based on where you are, based on other demographics. For example, age. You know, people my age or even a little bit older might want to have a warning a little bit earlier because it might be they cannot react as quick as the young kids, right? So these kind of things. And so this goes all in there, and we can test it actually there. We get live information back from operating that, and that's really, really valuable for our research because it's end to end. So in that lab, we have 7 radars running right now. So we started out with 4 in Oklahoma. We grew that up to 7 through support from industry and private-public partnerships. It operates year-round. We get, there's real-time information that goes out, and we get this out to first of all, local emergency management, the National Weather Service, and actually some of the TV stations. For those of you who live in the Midwest, you know that TV stations are a really important broadcaster for severe weather information, and you have to work with them. And then obviously we archive all this data to make it available for other researchers who are interested in that data. You see a little bit of where this is in Dallas. And then just a little bit about the private-public partnership. Again, you see the guys pointing at the radar. That's Juan Ortiz. He did such a good job that he's now the head of emergency management in San Antonio in Texas. So they lured him over there. But he was a great partner during the time he was in Dallas-Fort Worth. And you see, so we had worked deals out. We say we're coming in, we're bringing you much more detailed information on weather. But what are we getting back? And so we have some of these partnerships. They built the infrastructure. Some of them built a tower. Some of them provided us land. Some of them provide us electricity, communication infrastructure to install and run our radars there. So that's kind of some of the things that go into how can we actually make our work sustainable? How can we make our ERC sustainable and continue our research? It's a little bit of a give and take because all of a sudden when you become operational, there's a bunch of extra things you not necessarily want to do as a researcher. But I tell you one thing, you get a lot of important value back from that, right? I told you about AWIPS. I tell you about we have, behavior information from users in severe weather and all these kind of things we can use now for our research. So that's I think it's worth the effort, I have to say. So convergent research. So here's, colors come out a little bit better now. Here's, the different research areas, right? So for CASA, we have social scientists, we have meteorologists, sometimes they want to be called atmospheric scientists, electrical engineers, and computer scientists. I'm pretty sure this is a different constellation for each, and every engineering research center, but that was our constellation. And you know, there's world-known, world-renowned experts in every field we had in the ERC that were really experts in their specific area. And here's the challenge. How do we get that expertise, how do we get this expert to contribute to a center where it is not necessarily about your particular research, where it is about integrative research, where you work with different disciplines together, where you have to learn new things. I never forget we had a discussion about architecture. Architecture is a wonderful word. If you ask 10 people in the room, you get 10 different answers on what architecture is, right? So you have to find even a common language about how these different engineers and scientists talk. They all speak English, obviously, right? But definition is important. There's a lot of challenges you have here to get your team together on that. And so a couple of things on how can you make this convergence, how can you make this convergent research actually happen? I think NSF did a wonderful job on saying you have to have a test bed, right? I don't know, I think Lynn Preston was kind of, you know, she was coming down very strong on us. And you know, it's always easy to say that in hindsight, but I think that was important. If you build something together, everyone is in the same boat and everyone is converging towards that test bed. You need a test bed, right? That's really important. And make your test bed. I've seen many ERCs and some of several test beds, some of a single test bed and so on. If you can have a single test bed where everything centers around, I would say that is the perfect solution, right? Because you can involve everyone. It doesn't always work. I understand that it really depends on what your topic is, what your research is on, but ideally that's good. Actually, also we didn't end up with a single test bed. Our students had their own test bed, which was a wonderful move because that was a great teaching experience of letting them run and taking care of being in charge of their own test bed. And we had some wonderful results coming out of that. And I'll speak about this in a moment. So community building, right? How do you get people to buy into this? How do you get your group of researchers? I think one of the biggest challenges, we all know that, you know, all of us who are faculty, it's always the thing we think about, you know, how can you make faculty do something, right? It's really hard. You cannot force people. So you have to think about other mechanisms, and some of that is ownership. Some of that is patience, right? And so you have to think about how you can get people really be passionate about what they're doing in an ERC and contribute on that, right? And sometimes you actually, to be honest, you have to make hard decisions, right? If you see that someone is not a team player and is not, you know, contributing to the greater good in your ERC, you really have to think hard if that's the right individual you have in your team, right? It can cause problems in the end, so that's something you have to keep in mind, and the leadership team of the ERC has to watch that constantly and be aware of that. So that goes into organization structures. I want to emphasize on system engineering in a moment also a little bit, because I think that's a really important process everyone should think about and should at least consider of putting in place when you build you know, test beds, large systems. That's important. And I think it's also something you should make the new normal for students, because they are the next generation that will become faculty, go out in the research labs and industry, maybe write an ERC grant at some point in time, right, or a proposal. I just want to give you this quick snapshot here from an end-to-end, this was the year site visits are the high-stakes site visits, right? Are they? I believe, are they still the high-stakes site visits? I think that was for us at least, so that's when your last round of funding comes in and all the stuff. And so here's just a schematic overview of our test bed, and each of these bubbles you see here was one of the highlights we could show, right? And I think that worked really in our favor. I'm not going to go into details, don't worry, I'm not going to bore you with that. But with that test bed, we had people from all different research areas, and even sometimes teamed and grouped together reporting about the highlights. And I think that worked really well for us, because then we could say, here's all the different aspects you work on, end to end. You see the sensors on the left-hand side, you see the end users on the right-hand side, and all the technical details in the middle, and could present how this works out. So again, another emphasis on the test beds. Community building. I think, so what you see on the left-hand side here in this graph is actually, we had 4 different thrusts, right? A sensing thrust, a distributing thrust, a predicting thrust, and an end user thrust. Now, what you need to stitch them together again is the test beds, right? Everyone has to contribute. Everyone has to work together. I had the pleasure to be hired into CASA to, you know, be that vertical guy here to get them all pulled together to build the test beds here and contribute to that. And so I think that there was an immense learning curve for myself, but that was really what led to convergence in this case, right? That's really important. What role does do the students play? I mentioned earlier, we had the students build their own test bed, right? And it was really good because, sure, there was advice, but there was not every morning, no one told them what the students had to do. They had to come up with their own plans, they had to come up with their own solutions, they had to come up with their own challenges, and not challenges, but they had to come up with their own structure and how they did these things. And I think that was a great learning curve for the students. And if you see where they are right now, I think they learned a lot because they all got really, really good jobs. So the other thing is breaking silos, right? Breaking silos and promote interactions are two important things you have to do, right? So we all like to be in our comfort zone. At least I think that's true for a lot of us. But we have to see how we can get people out of the comfort zone. And there's mechanisms that you can use. We heard about teams and organization structures earlier today, but I think it's hard to say that's the cookie cutter approach because, ERCs are very different. They're composed of a lot of different teams, but you have to think about what are the mechanisms, what are the incentives you want to put in place. And one thing, this is an old slide, my good friend Jim Caruso, who was assistant director at SAIS until a couple of weeks ago here at NSF, put together when he was involved in the ERC. Don't look into the details of the organizational structure. I don't want to bore you with that. Again, I don't know if this is not the cookie cutter solution. But what you have to figure out is down in the research trust, that's where you have the heavy lifting, right? This is where the innovation comes out of your ERC and so on. And you have to, that is kind of the team you have to worry most about. They have to be cared the most, but they also have to be responsible, that they made responsible for delivering the packages, whatever they have to provide to make your ERC careful. So that's what needs quite a good structure and some quite good management. The new normal for students, right? You will educate the next generation of engineer scientists who will in many cases become the leader in this area, right? Because they get this wonderful education in the ERC. But I think you would do everyone a great favor if convergent research becomes kind of ingrained into them, because then they go out into their faculty positions or in their industry labs, and they will make it part of their work culture. And I think that would really be a nice multiplier if we get that. I mentioned before, students had their own test bed. Here we see some of the students. On the left-hand side, you see Francesco Junient, who runs his own radar company by now, talking to students from the School of Meteorology in Oklahoma when we were putting the radars together, right? There's a bunch of students with me. There's actually students from Puerto Rico who came and stayed with us at UMass. And they were working because we were the students collaborated closely on the test bed, which then was eventually deployed on the island of Puerto Rico, their student test bed. A couple issues I want to leave you with before I end here. Is actually, systems engineering is important from my point of view. Changing culture is important, but it's hard, right? That's not something you do overnight, and actually also incentivizing faculties is something you have to keep in mind. And think about how you can do that. So on the systems engineering side, I don't want to bore you too much with the words, but one of the things is really what we did is we put out requirements. What will our system be capable of once we have built it, right? And that was page 1 of our systems research, our systems requirements document, right? So everyone could look there. And everyone, if there was a doubt or anyone, it was always look at page 1 or page 2. There it's written down. This is what we're shooting for, right? Were we overshooting a little bit? I have to admit, yes, we were. Was that a bad thing? No, because we achieved a lot of good things, right? But you have to have these common goals everyone knows about and everyone is bought into, everyone has bought into. So that's important. And when you do systems engineering, when you look into different approaches, and some of you might be a much more of an expert than I am, we have realized that spiral development really worked for us because it's dynamic. It helps you with living with changes, where you can make certain changes because we're so close on the cutting edge with our research that we sometimes don't know exactly how things will turn out. So keeping your system flexible and making changes that don't make you have to go back to the drawing board is time that's wisely spent in the aftermath. I'll give you one example. The 4 radars you see there when we produce them on the left-hand side, they have incredible pedestals. They can turn in like crazy speeds, crazy acceleration, crazy deceleration. They're extremely expensive. But it was a great investment because it gave us a lot of flexibility in terms of simulating what we could do with electronically steered beams in the future. Electronically steered radars, so phased array radars for weather observations, weren't ready at the time. They're becoming ready now, slowly. But they weren't ready at the time. So what we did is, we said, let's go overboard on the mechanically steered radars with the how we can, steer them, and see what we can do with such systems. And we could learn some really, really good lessons. It wasn't the whole deal because we don't had to deal with some of the effects you have with phased arrays in terms of how your beam warps and all these kind of things, but it helped us a lot. It's a very specific example. I understand that, but think of if there's something that you can translate out to the work, to the ERCs and the tasks you're planning for your research. Where can you go and think, as far as possible out to get the most benefit and the most flexibility from your system? I also, do you know what the picture on the left-hand bottom is? Yeah, it's the Wright brothers with their first flight. I cannot think of the name. The guy who writes all the history books has a wonderful book on the Wright brothers, and I think of his name in a moment. McCullough has a really good book on the Wright brothers. They were awesome systems engineers, and they were great innovators. If you ever get a chance, read that book. They were the first one to do motorized flight, right? We all know about this, but they had to learn how to steer, how to make flexible wing surfaces to steer a plane. They had to build engines. They had to become pilots, right? I mean, you couldn't go out and hire a pilot at the point in time because they weren't really motorized planes at the time, right? So they had to do all these things, right? And I think that's one of the things when you're really at the cutting edge, when you do innovation, you have to think about what you have to do, what you have to put in place, right? And so you're looking here now at not only, but it's also the research side. I mean, you also have to then think of, what kind of research is important? What research do we have to focus on, right? And so I think even so, this is this is more than 100 years back by now. This is a really important and interesting lesson you can learn and very entertaining, I have to say. There's a lot of things that might be obvious to you, but I thought I'd mention it anyway. Courses, right? Again, coming back to the students, co-taught, cross-listed, right? Make convergent research the normal for your students. Don't have them just take ECE, just take computer science classes, just take atmospheric science classes. Co-teach classes, so they sit together and they learn about the research, about the problems, the challenges, the basics that are going on in the other research areas. Think about any innovative programs you can put in place, right? Master, PhD, joint programs. Think about where you can now reach out to your stakeholders and work with them for internships and so on. And I think that are really important things to keep in mind. And I think one of the things David McLaughlin at the time made kind of a rule is workshops. There are no workshops where only one discipline is sitting together, right? If we're going for a meeting somewhere, every research thrust has to be present, right? If you want to meet 3-4 people, right, that's fine. You can sit together and talk about your core technical problems. But for larger goal meetings, everyone has to be on the table. So that was one of the things that was important and really helped with the culture, right? So the changing culture, I admit it's difficult, and I'll be done in a minute. It's hard to break these silos. It's also a little bit of, I sometimes see that even these days when it comes to committees, right? If you want to bring someone from the outside into your committee and so on, right? Think about this, be creative. Make your administration to be more flexible on this side. It'll pay off. Junior faculty are the ones you really have to think hard about because they have to be protected on one side because, they're measured towards their tenure, but you also want them to be doing, convergent research, which is a little bit of a, pulling on both ends, so to speak, because it's not necessarily in their core interest. How can you reward them? And then also proven collaborators in your team. I think that will pay off. And again, finally, for all these things, you really need buy-in from your administration. So if you're thinking of submitting a proposal, Go out to your deans, go out to your department heads, go out to your administration. Talk to them now about the things you have in mind and get their support. Because teamwork can always happen, right? But getting the right teamwork done is really important. So I think I'll skip over the conclusions because I'm running over time a little bit. And while I'm doing Q&A, I leave you with that slide because one of the rewarding things is then when you really see that your radar data is showing up on the news channel, that you're mentioned in 4 or more NRC reports, you really realize that your convergent research and all the things you were doing that you didn't have in mind when you started working for an ERC is really paying off. Thank you very much for your attention. Sorry for going over time. I have to say, two more words. I want to thank Sandra Cruz-Paul and Deborah for inviting me today. It was really a pleasure. We've known, Deborah actually mentioned me getting wider. She was kind enough to talk about my wisdom. I'm not sure if that's true. But thank you for inviting me. It's been a joyride working with the ERC team over such a long time. And I want to thank all the folks back at all the institutions who worked with me in CASA. It's been a really great experience and a wonderful time. Thank you.
Speaking of lessons learned, if you were to do this all over again, what would you do differently?
What would I do differently?
Because I heard a lot of success stories.
Yeah.
I want to learn more about areas that you could have improved.
So, you know, knowing the things you don't know is always the problem, right? So being able to anticipate things. I think I mentioned that, and that, you know, we got lucky with finding Juan, who pulled our test, or helped us pull our test bed down to DFW. We didn't do a perfect job in planning for the time after the NSF funding ends, right? We got lucky, and it was a little bit of a struggle. I'm not sure if there's still a topic. I know Lynn was always big on the shadow of the valley of the death, right? I don't know if you've seen these slides about, you know, where your funding ramps down, and you're not necessarily ready to attract additional funding. How do you get that, right? You cannot start thinking about this early enough, right? That's really important. I think I have to stop now, so I'll hang out a little bit and be around for further questions. Thank you very much.